Operating an industrial wastewater system, whether it is a standard water treatment plant, an effluent treatment plant, or a zero liquid discharge facility, presents a strict chemical balancing act. Injecting the incorrect chemical coagulant creates an immediate chain reaction of operational failures. You will see plummeting water clarity, massive spikes in sludge generation, and rapidly inflating daily operating costs. The central objective of your plant is to precisely match the raw influent characteristics, specifically your starting pH, your baseline turbidity, and your oil concentrations, to the correct chemical profile. This matrix outlines the 4 primary coagulants engineers rely on: polyaluminium chloride, aluminum sulfate, ferric chloride, and ferrous sulphate. To make an empirical selection, we evaluate each across 4 rigid parameters: baseline efficiency, optimal pH, target application, and operational drawbacks. There is no universal best chemical in wastewater treatment. Coagulant selection is a strict optimization problem defined by the exact pollutants you need to remove. Achieving a compliant discharge requires abandoning trial and error and strictly balancing these chemical traits against your plant's operational constraints. We begin with the aluminum-based category of coagulants, which are the standard utilities for general municipal treatment and standard turbidity removal. Aluminum sulfate, commonly known as alum, is the historical baseline choice because it is highly economical and widely available. Its target applications are straightforward: moderate turbidity removal and standard municipal water systems. Looking at its baseline performance on the matrix, alum achieves a respectable efficiency range, clearing 70 to 85% of suspended solids. However, it comes with a strict operational constraint. Alum requires tight pH control to function, demanding a narrow window specifically between 6.5 and 7.5. It also carries 2 physical drawbacks. Alum produces high volumes of heavy sludge, and its chemical reaction slows down significantly if the influent water is cold. This brings us to polyaluminium chloride, or PAC, which operates as a high-performance, modern upgrade to the traditional alum baseline. PAC works by rapidly forming floc, the process where microscopic suspended particles bind into dense clusters that settle out of the water column at high speed. This speed makes its target applications heavily industrial, specifically treating high turbidity water, vehicle wash water, and industrial surface water. On the comparative matrix, PAC pushes efficiency up to a 95% maximum, while maintaining chemical stability across a much wider pH band than alum. Crucially, its major operational advantage is generating significantly less sludge, immediately solving one of alum's most expensive drawbacks. The primary limiting factor for PAC is purely financial. It carries a higher upfront cost per liter compared to traditional alum. But when factoring in its speed, its wide pH tolerance, and the drastic reduction in sludge disposal costs, PAC is mathematically superior for high turbidity industrial applications. Standard aluminum coagulants lose their efficacy when confronted with extreme industrial effluents. For these environments, engineers deploy iron-based coagulants. These are specialized heavy lifters, formulated for specific, difficult pollutant profiles. Ferric chloride is the primary choice here. It is designed explicitly for oily wastewater and heavy industrial effluents. It also carries a highly effective secondary capability: aggressive and reliable phosphorus removal. Looking at the dashboard, you can see ferric chloride's operational flexibility. It remains active across a massive pH spectrum, functioning anywhere from 4.0 to 11.0. Within that wide band, it sustains a high efficiency rating, removing up to 90% of its targeted industrial pollutants. But it introduces a severe operational danger. Ferric chloride is highly corrosive. If you pump this chemical through standard plant infrastructure, it will eat through your lines. Using ferric requires mandatory installation of specialized, non-corrosive piping and handling equipment to prevent facility degradation. There is also a visual risk to your final effluent. If operators overdose ferric chloride, the excess iron will tint the treated water a distinct yellow or brown. The final coagulant in our model is ferrous sulphate. This chemical serves a highly specific niche application, stripping out specialized coloration from textile and dye wastewater. It provides the secondary benefit of phosphorus reduction, and does so at a very economical price point. On the matrix, ferrous sulfate demonstrates its core competency, achieving an 80 to 90% clearance rate specifically for color removal. Its critical operational flaw, however, is that it completely fails to activate in low pH acidic environments. To bypass this flaw, operators are forced to implement a mandatory workaround, artificially driving the pH up to the alkaline side by dosing the water with lime. Adding that lime creates a compounding problem, hitting the plant with a heavy sludge generation penalty. Iron coagulants demand high operational discipline regarding corrosion control and pH adjustment. But for oils, dyes, and heavy industrial pollutants, they are the only viable options. Now that we have established the chemical properties, we can reverse engineer our selection process by looking directly at the raw effluent profile. This decision tree maps the logic. High oil or industrial loads dictate ferric chloride. Textile dye requires ferrous sulphate with lime. For moderate municipal wastewater on a budget, alum is the economical path. For high turbidity and low sludge, PAC is optimal. But there is a vital engineering caveat here. This theoretical matrix only provides a baseline starting point. It is not the final operational answer. Theoretical selection must be backed by empirical validation. This is done through a mandatory procedure known as the jar test. The jar test utilizes a benchtop mechanical stirrer to simulate the plant's exact real-world flow conditions on a microscale. It allows engineers to physically observe flocculation speeds and sludge settling times. Because daily wastewater characteristics fluctuate based on production schedules, the jar test is required to pinpoint the exact dosage of your chosen chemical for that specific day. Applying an incorrect dosage, even if you have selected the mathematically correct chemical, will cause the process to fail, leading to outcomes like the yellow water associated with a ferric overdose. Getting both the chemistry and the precise dosage right guarantees maximum water clarity while driving down your overall chemical consumption. This precision minimizes your sludge handling costs and ensures that your treated water is ready for seamless environmental discharge or zero liquid discharge reuse. Mastering coagulant selection and enforcing empirical testing shifts a wastewater plant from an expensive, reactive burden into a predictable, optimized system. Drop your specific plant challenges in the comments below and subscribe for more industrial water treatment breakdowns.